Good morning, all of you. Sorry for the delay. We will start our discussion today on design for X. Okay, X stands for many things. Generally in algebra, okay, we use the symbol X as a variable. So design for, we are going to discuss about many other things. That X is going to be filled with many things. So what do you mean by designing for X? What else to consider? So here I want you to do two things. Let us see what we have accomplished, what designs we have learned so far, okay, and what else is missing, or what we are planning to learn today. Let me take a very simple component, a simple product. Let me take this table. Let me take this table. Is it okay? So the task is to design a table. The task given to you is to design the table. You have done functional decomposition, you have done all that. Okay. Now, you have completed embodiment design also. Let us assume you have accomplished up to embodiment design. Now, at this stage, you have designed a table. At this stage, what will you have? At the end of embodiment design, what will you have? Will you have a table?
A drawing.
The detailed drawing of the table you will have. Is it okay? The detailed drawing of the table you will have. That means when I say detailed drawing, will it have dimensions? Yes. So that is the important step in design. So you will have the dimensions of various parts. Meaning, let us say, what are the critical dimensions involved in designing this table? But beautiful. The length of the top portion, width of the top portion, the total height of the table. Is it okay? From the floor level, what should be the height? What are the other dimensions? Pardon, sir? Somebody said? The thickness of the top flank. Pardon? Thickness of the rod. Is it a rod? It is a square extrusion. So first, no, it's not cubical. It is a square extrusion. It is an extrusion of hollow square cross section. It is called a box section. Okay. Here, is it a single dimension? Is it good enough? I should give this dimension, this dimension. This is about 25 mm. This is about 25 mm, and the thickness is about 2 mm. 1.5 mm or 2 mm. Thickness is. What do you mean by thickness? I mean, when you take a section, it will be something like this. It will be something like this. It's not a solid. It is not a solid cross section. It is a hollow cross section. Okay. This thickness is to be. So by dimension, I mean all this. So what do you mean by the dimension of this? You have accomplished embodiment design. Meaning what? You have decided the height. You have decided what should be this width, what should be this breadth. Then you have decided what should be the, okay, this is, I call it as A. This is also A. This is T. Okay. Say A is 25 mm and T is 1.5. At the end of embodiment design, you have arrived at all these dimensions. Of course, there are a few more minor details. let me confine to these 6 dimensions. Let me confine to these 6 dimensions. Of course, 3 are given here. A, it is equal, so it is only 5. A, and T. And the other 4 dimensions that you have talked about are the width, breadth, the total height, and the thickness of the plank. Now, I am going to ask you a few questions. On what basis did you decide the breadth of the table? The breadth of the table, as I said, is about 700 millimeter. B, D, T, H, H. What is B? B is 700 mm. D is this dimension. Are you able to understand? D is about 500 mm. Thickness of the plank is 12 mm, and the height is about 900 mm. I have just measured. Take it from me. These are the dimensions. Now my first question to you is, how did you decide? On what basis did you decide the breadth to be 700 mm?
Customer requirement.
Pardon?
Customer requirement.
Very well said. Customer. Did the customer say that I want 700 mm breadth? What did the customer say? I should be. You are the customers of these products. You are the students. Students are going to use these products. What did the students say? This is a table to be used in a classroom. So students said, I want to probably keep my things comfortably. At the same time, keep my notebook and then write comfortably. Some other student would have said, probably I would like to rest my head also on it and then lie down for a moment. Only a moment. Okay. So this might be another customer requirement. Do you understand? So from these customer requirements, you have arrived at the breadth and depth. You have arrived at the breadth and depth. Okay, he will keep one book here, another notebook here. He must be able to rest his hands. Probably somebody would like to keep a bottle of water here or a glass of water here. So for all these things, this 700 by 500 will be convenient. So from the customer requirement, I have arrived at a functionally satisfying top area for the table. A functionally satisfying top area for the table, which is 700 by 500 mm. So from the functional point of view, I have decided these dimensions. Yes or no? Right. How did you arrive at this height? 900 mm. Why not 1000? Why not 600?
Height of the chair.
Height of the? Okay. So when the height of the chair is, the height of the chair will be about 600 mm from the ground. The sitting part of the chair, it will be about 600 mm from the ground. When somebody sits in a chair, he should be able to comfortably rest his hand on the table. So that determines, again, this 900 mm is determined from the functionality of the part that is being designed, functionality of the product that is being designed. Is it okay? So this 900 mm decision is taken based on the functionality. If it is 1200, probably when I sit, the table will come to this level. I won't be comfortable. If it is 600 mm, it will not be a table, it will be a teapot. Okay, I may have to lean and then ride again, I am not comfortable. Is it okay? So from the functional point of view, I decide this 900 mm. So it is from a functional point of view, I decide this 900 mm. Okay. All these decisions were taken based on the functional points of view. Let's go further deep. Suppose this thickness 12 mm. How did you decide at this thickness of 12 mm? Is the customer really bothered? Is the user of the table really bothered if the thickness is 12 mm or 6 mm or 2 mm or 1 mm? For the writing convenience, will it influence it? Yes or no?
No.
Then why 12 mm? Why not 5 mm? Why not 6 mm? Hey, there must be some logic to the decision. So, somebody may suppose there is some fault in the light. I may decide to stand on this and then do some repair. It should not collapse. Of course, the table is not, as a product, it is not meant for me to stand on it and then repair a light. But please believe me, when you design a product, I think I had already told it earlier, when you design a product, you should also design it for abuse. Because many times products are abused. Okay, you drop your cell phone. Many times I have seen students throwing cell phone and someone else catching it. This is clearly abusing a cell phone. Have you done it? Throwing cell phone and catching, yes or no? Yes. Throwing cell phone and catching, you casually do it. But should the cell phone be designed for it? Yes. Every product design is not only used, the products designed are also abused. So as a designer, you must design not only for product usage, but I think I have already talked about it. You should also design a product for product abuse. Okay. So many times systems are overloaded. So I should design it to withstand certain load. So I decide based on the load considerations. So this is from the point of view of design for strength. What are the other three dimensions? How are they decided? They are designed for functionality. Now, this thickness 12 mm is designed for strength. Then, this A, 25 mm, the dimension of the legs. Are you bothered if the dimension is 10 mm? From the functional point of view? No, you are not bothered. But it is a column, it should not buckle. So, this is also designed for strength. So, these dimensions are also decided for strength. So, you have seen two different considerations in our embodiment design. One is the designing for the functionality, the other one is designing for strength. Of course, this designing for strength you will study in detail in your mechanical engineering career. In your mechanical engineering career, you will study a paper called Strength of Materials. Then two papers called Design of Engineering Components, Design of Transmission Systems. Then you will study another paper called Finite Element Method. All these papers exclusively deal with design for strength. How to design something so that it is strong enough. That is the whole objective. Design for functionality, you will study again few papers. Something called theory of machines. Okay. Or you will study about different mechanisms in your drawing. All these papers teach you how to do some how to do some functional design. There are many issues in functional design. Okay, that also you will learn in your engineering career. Now, is that the end of it? There is something called design for functionality. There is something called design for strength. That's all. Or do you have any more designs? We have many other designs, and all those things we are going to see together in this class. For example, there is something called design for aesthetic appeal. Is it important? Yes, it is important. Any product design must be very appealing to the aesthetic appearance is very important for any product. It should have a good looks. It should have a pleasing appearance. So, you should design for appearance also. You should design for something else called ergonomics. Design for ergonomics. Okay. See, why not the gear change lever? Why don't we have it on the roof? Why should be on the accessible to the left hand? Because it is easy to operate that way. Okay. Where to locate the steering column? Exactly at what height should I have? You have now in modern vehicles we have adjustable steering column. Because I can have it at my convenient, ergonomically convenient location. Otherwise my hands will pain. So this is called design for ergonomics. For example, in all the machines, invariably the stop button will have what color? Red color. Because nobody is bothered whether you know how to start a machine or not. But you should know how to stop a machine. That is very, very important. Many times you should know how to stop something. Many times we start something without knowing how to stop it. Many habits they stick to us because we don't know how to stop it. In machine design, the most prominent button must be what? The stop button. In any system, the most prominent button will be stop button. Okay, in mains, the stop button is painted red. In compressors, the stop button is painted red. In all the machines that you can see, you can go to the sim lab and then see some CNC machines. The CNC machines will have a prominent, very, very obvious, the first thing that you can see is the stop button and that will be painted red. These rules are articulated in the design for ergonomics. So what are all the X's that we are seeing? Two things we have already studied. Design for functionality, design for strength. Then the third thing that I talked about is design for appearance, design for ergonomics. But today I am going to concentrate on two things. I am going to concentrate on design for manufacturing and design for assembly. That is of immediate relevance. Anything that you have designed, what should happen next? That should be manufactured. And the parts manufactured, what should happen to them? They must be put together. They must be assembled. Okay. If you don't take these aspects into consideration, somebody will come and say, "Sir, your design is fine, but it is fine on paper, but I cannot make it." If somebody says that, it is of no use. So, what we are going to see today, spend another 1 hour discussing, is design for manufacturing and design for assembly. Is it clear? So and then I have few videos about a typical assembly line. We will see that and then call it a day. Next slide, please. Basically, there are different manufacturing processes. I am going to take up some few typical cases. I am going to take up injection molding because most of the polymer parts, plastic parts that you would have seen already, they are manufactured by injection molding. So I'll take up injection molding, I'll take up casting, I'll take up machining. Because what are the three basic manufacturing processes? Casting, what? Metal cutting, metal casting, metal cutting, then metal forming. Okay. Molding is again melting and pouring. So metal casting is one major. You should never forget. As mechanical engineer, you should never forget. Melting and pouring is called casting or molding. Then the next category is metal forming, in which either you heat it and then deform it, or without even heating you can deform it. You change the shape by repeatedly applying huge amount of force. That is metal forming. Okay. The third category is metal cutting. So these three important categories, we will see how that is taken into consideration. Now the first thing is, when you are using injection molding, I am going to say the same thing on the opposite way when we talk about casting. When we talk about injection, first you should understand what the manufacturing process is. Injection molding, how manufacturing takes place, can somebody say? Because many of you have written in your assignment that the plastic components of the various toys are manufactured by injection molding. What is injection molding? Fine. See, what you do is, you melt the polymer. You have a polymeric compound, you melt it. You have a metallic cavity. It is usually made up of steel. You have a steel metallic cavity. Now this molten plastic, you inject into the cavity under pressure. This is called injection molding. Do you understand the process now? Are you able to visualize? Then what will happen? Since there is a metallic cavity, all the heat present in the polymers, what will happen to that? So that will be absorbed by the metal mold. And what will happen to the polymeric part? It will solidify. So you cool it, take it out and then use it. Most of the polymeric components are manufactured like this. Suppose you take, have you ever wondered how do they manufacture the plastic bucket that you use in your house? Forget about the handle. Handle is manufactured separately and they are assembled together. All of you have seen a plastic bucket. Yes or no? How is it manufactured? In fact, my next assignment, I am going to give you 2 assignments, weekly assignments. Don't worry, it will take at least maximum 1 hour if you work in a concentrated fashion. Okay. So I am going to give 2 assignments and you have to submit it by next Tuesday. Is it okay? 2 assignments each not exceeding 2 pages. Front and back. Okay, each not exceeding 2 pages. But please make it a point to work out independently. Now, have you ever wondered how they manufacture the plastic bucket that you have in your house? Now, the secret lies at the bottom of the bucket. Okay, all of you go home and then see the bottom of the bucket. That will prove, that will explain how a bucket is manufactured. Now, the bucket is manufactured something like this. I'm sorry, I'm not very good at drawings. So this is a a metallic mold. This is a metallic mold. This is a metallic mold. Is it okay? These parts are filled with steel. These are steel parts. And you have a cavity here. It is axisymmetric. Meaning, what is the shape of this cavity? The shape of this cavity is the shape of the bucket that you are going to get. Are you able to visualize? Sir, na varayirudhu pesuradhu purida ungalku purida? Okay. So this cavity is the shape of the bucket. Now here you have a piston. You have the molten polymer entering in, and the molten polymer is pushed inside. The molten polymer is injected inside. That is why the name injection molding. That is why the name called injection molded part. A typical example of an injection molded part is the bucket that you have in your house. Is it okay? Now what will happen? So after some time, the molten polymer will solidify. Okay, the molten polymer will solidify. In fact, here also you have the mold wall. This actually continues. And what will happen? There will be this portion is cut and then taken out. There will be a small stem which is protruding outside, that is cut. You can see that mark at the bottom of your bucket. You can take and then tilt it back. You will see a small mark here. That is where the molten polymeric material was entering into that. All injection molded parts will have this mark. A small plastic ball will have this mark. Have you seen a plastic ball? I am not talking about some other ball. Plastic ball. Okay, which makes sound. Okay, plastic ball. Okay, that will have a mark. Plastic bat, cricket bat, which small kids use, they will have this mark. Any injection molded part, any injection molded product will have the small mark, which you can see in your. That is a telltale for an injection molded component. If you see that mark, you should immediately recall that it is manufactured by injection molding. Are you able to understand? Okay. Now, if you are designing a product for injection molding, now on the same count, I would like to ask you one thing. Why all the buckets that I see, why all the buckets, they have a shape like this? Why I don't see any bucket at all, almost like this? Will it not be more elegant? Okay, or I never see any bucket which is like this. Probably I would love to have a bucket manufactured like this. Can somebody say why? Oh, wait a minute, let us listen.
Water level குறையும் போது சார் எடுக்கிறதுக்கு வந்து அந்த பெரிய பக்கெட் இருந்துச்சுன்னா வந்து கொஞ்சம் கம்மியா தான் வரும். இதுனா நமக்கு நிறைய வரும். அதனால
No, but see, my traditional pot is something more similar to this. My traditional pot, I don't see any bucket like that. Why? What? Good thinking. It will occupy more of floor spacing. Okay, it's not okay. It's not very convenient to Carry, no, I don't agree. Now one thing is, when I mold it by injection molding, okay, it is easy to withdraw the molded part if it has a shape like this. Imagine what happens. It is solidified now. It is solidified now. Okay. Now what will happen? Now I can very easily, I need not disturb this at all, I can very easily pull it out like this if the shape is like this. Are you able to appreciate? If the shape is like this, then I don't say it cannot be manufactured, it cannot be pulled out like this. The solidified component, it cannot be taken out like this. I'll tell you, I'll end this discussion with another question. Okay, they also manufacture, what do they call it as? Kodathuk English enanga? Bottle. Plastic la kodam pandranga illaya? Plastic kodam. Plastic kodam. Adu English ache. The plastic one, that is also manufactured by injection molding. Then how will they withdraw it? After solidification, how will they withdraw it? Blowing acid as injection molding la, that is called, there is something else called blow molding. That is an altogether different process. I leave it to you. I leave it to you. Think about it. Okay. No, I am not going to answer it. Why don't you search and then find out? Okay, right. Now my objective here is, when I am manufacturing a part, when I am designing a part, which is going to be manufactured by injection molding, what are all the things that I must consider? First, minimize the section thickness. Why should I minimize the section thickness? If the section thickness is too large, it will take longer time for it to solidify completely, because cooling time is proportional to the square of the thickness of the parts, and if the cooling time is more, I have to wait till the whole thing cools down. Okay, my productivity goes down. Instead of manufacturing 10,000 parts per day, I can manufacture only 1,000 parts per day if the cooling time is more. So that will increase my cost. So if you are manufacturing by injection molded part, try to have the thickness as small as possible. Next slide please. Now, provide a draft. You have to provide a draft, because that makes the mold removal easier. You have to provide a draft. Instead of this is much preferred, because the mold removal will happen much more easily. Are you able to appreciate? Next slide please. Now, don't have a sharp corner. In any design, you should never have a sharp corner. I used to say, a sharp point is also a weak point. A very sharp point is also a very weak point. A classic example is, if you make your pencil very, very sharp, what happens? The moment you start writing, what will happen to the pencil tip? It will break. Because you are applying certain force, which is the writing force, and your tip is so sharp, it is not able to even withstand that force. So a sharp point is also a weak point. And you should not have a sharp points in your design. You should always provide a radius. Next slide please. Now you should have some minimum thickness, distance between ribs, because there is going to be metal in between and that should not get overheated. So the ribs must have some minimum thickness and distances between them. Next slide please. So when you have bosses, these are called bosses. You should position them carefully. Okay, and you should keep the section thickness uniform around bosses. What will happen if the section thickness is not uniform? The section thickness is large at some place, it is very small in some other place. If the section thickness is very large in some place, then there will be molten metal remaining in that place because solidification would not be complete. So, suppose you have a huge thickness here. You have a huge thickness here. So, just after injection, this will all be molten plastic. Who will absorb all that heat? This poor fellow must absorb. Here is only you have metal. This must absorb all the heat. Heat transfer will be very low because this will be at an elevated temperature. On the other hand, if I have a uniform thickness throughout, the heat absorption will be more easily accomplished and you will be able to improve the cycle time. Are you able to understand, or am I going fast? Shall I proceed? Next slide, please. Now, similarly, don't change the cross section suddenly. Later on, you will study a phenomena called stress concentration, wherein again a sudden change in cross section is not at all preferred in engineering. In engineering, you never change the cross section very suddenly. A gradual change is always preferred, even from the stress point of view. Now here again, this you should never do. This is much better. This is best. How this is best? This is better because the change in cross section is not sudden. This is best because the thickness remains same everywhere. I have removed some material here, so the thickness everywhere remains same. Here you have a large thickness and here you have a very small thickness. In between, the thickness varies uniformly. So the first one is very bad, the second one is okay, the third one is the best. So these are all design changes that are accomplished, that are done to facilitate easier manufacturing. So different manufacturing processes, they have such requirements. So injection molding has these requirements. Later on I am going to say casting has these requirements. Metal cutting has these requirements. We will quickly see this. Okay, all that I want you to appreciate is, depending on how the material, how the part is going to be manufactured, I may have to make some adjustments in my design, just to facilitate easier manufacturing. Next slide, please. Next. Right. Now this is by sheet metal formed parts. Now many parts are manufactured from sheet metal. Many manufacturing parts are manufactured by what is known as sheet metal. Now the raw material is a metallic sheet. Now what you have is, you have two dies. This is again a metal forming process. You have two dies which come and then hit over the raw material. The raw material is shaped to the required dimensions. Shape and dimensions. So this is one type of metal forming operation. Okay. Of course, you'll study about these forming operations in detail later. Only after studying these forming operations, these manufacturing processes, only after understanding these manufacturing processes fully, you will be able to do design for that manufacturing process. So what I'm trying to do is not to teach you manufacturing processes and all that. I just want to impress upon you, there are many other considerations in product design. Not just functionality is good enough, not just strength is good enough, there are many other considerations which should go into a good design. Next slide, please. For example, you have a punch you hold, and the punch you hold again talks about it brings to probably in my next lecture. I am planning to hold at least 2 more sessions before we conclude for the semester, before we conclude this entire paper. The next lecture is going to be on what is known as GD&T, dimensioning and tolerance. Now one thing that you must know, suppose I design a shaft. So I design a shaft in such a way that the diameter is, say, 25 mm. I design a shaft. I say the diameter is 25 mm. Okay, are you able to see this? Okay, fine. The diameter of the shaft is 25 mm. Now, please take it from me, there is nothing called exactly 25 millimeters. If I give a design in which I just say the diameter of the shaft is 25 mm, people will throw it back to me, because the manufacturing engineer will tell me back that there is nothing called exact 25 mm. What do you mean by 25 mm? If I measure the diameter with a scale, the diameter will be 25 mm. If I measure the diameter with a vernier caliper, the diameter will be this. If I measure the diameter with a micrometer, the diameter will be this, or rather this. If I measure the diameter with a much accurate equipment, the diameter will be 25.110. If I find a much more accurate equipment, the diameter will be something else. Are you able to appreciate my point? There is nothing called exact dot 25 mm diameter. It depends on the accuracy with which you want to measure it. So when I design a component and say the diameter is just 25 mm, my design is incomplete. I should say the diameter must be plus 0.05 minus 0.08. Every dimension in my design, I should provide a tolerance band. What is the meaning of this? The diameter can be anything, but the diameter must be more than 24.97 and it should be less than 25.05. So here I am not specifying a single value, but rather I am specifying a range of values. This is called tolerancing. What is tolerancing? I tolerate variation. Why do I tolerate variation? Because nature doesn't permit things to be identical. I don't know whether you know it or not. Your left off is not your right off. You may look very symmetrical. You may look very, very symmetrical. But please believe me, there is a lot of asymmetry. Okay, even if you stand before the mirror, you can see that your left off is not your right off. Your ear may be slightly longer here, shorter here, or nose may have a more curve here and not here. Every individual. Nature doesn't favor identical things. Nature believes in variation. If a manufacturer set 10,000 components in a lathe under identical conditions, all the 10,000 components will not have the identical dimensions. There will be variation. Okay, now since change is natural, being different is natural, I must specify how much of variation I am going to tolerate. So that is specified by what is known as tolerance. I'll talk about it in detail later. So every dimension, it should be specified a tolerance value. Every dimension must have a tolerance value. Now for press components, it is preferable to give as large tolerance as possible. Generally, any designer must resist the temptation to reduce the tolerance. Generally, you must provide, in any good design, you must provide as large tolerance as possible. Next slide please. So similarly, here you should not have you should have a minimum radius here, otherwise it cannot be made. The minimum radius must be 0.338 of the thickness. The minimum radius must be equal to 0.38 of the thickness. Next slide please. Similarly, when you have a bending taking place there, okay, the bending height has a limitation. Next slide please. Similarly, when you are punching hole and when you are bending, the bending radius must have a minimum value, and also you should position the holes away from the bends. The hole must be as away from the bend as possible, because the hole is a section of weakness, and when bending takes place, bending may not take place at that section. It may prefer to bend at a weaker section. Next. Again, the openings must be kept away from the bends, because this is a very weak section. It is difficult to bend a strong portion when you have a very weak portion here. It might break that. Next slide please. So if you design a punched hole like this, on paper it may look nice, but when you manufacture, it might bulge here. Are you able to appreciate? When I punch a hole, the material may get bulged here. So you should foresee. A designer must foresee these problems, and then you should design, either you design it like this, or you remove the material here, provide it as an opening. Next slide please. So there are many such considerations in design for press metal components. Next, continue sir, quickly continue sir. Next. Now, this is for when you are designing parts for casting. When you are designing parts for casting, see, in casting we have, as I told you, we are going to melt the metal, pour into a cavity, and in casting you should never forget this. The least melting point constituent is going to be the one which is going to solidify the last, and that is going to be the weakest part of any casting. I'll explain whatever I have said. In any alloy you have more than one metal. Which will be the part which solidifies the last? The least melting point constituent will be the part which solidifies late, and that will constitute the line of weakness. So when you have a thickness like this, all the good metal which has high melting point will solidify. Here also all the high melting point constituents will solidify. And what will happen here? Here you will have the last to solidify. The last to solidify is the weakest part. So the weakest part will align like this, and that will cause a lot of problem. The idea is you should ensure uniform solidification. To have uniform solidification, what should we have? You should have uniform thickness. So I should have a uniform thickness so that solidification takes place simultaneously. Next slide please. Again, you have to provide a draft angle. Otherwise, you would have prepared the mold. After preparing the mold, the pattern is to be taken out. Have you prepared the molds?
Yes, sir.
In your lab, you would have prepared molds, isn't it? After preparing the mold, the pattern is to be taken out. Because in the place of the pattern only you are going to pour the molten metal. So how will you take out if you don't have the draft? This angle is called the draft. So liberal draft must be provided so that you can take out the pattern. Next please. So here again the section thickness is to be kept uniform. You have a very small thickness here and a very thick section here. It is not good because that will lead to uneven solidification and associated problems. Next slide please. So again, a large fillet radius is always preferred. A liberal fillet radius is required. Next. And similarly, ribs are to be staggered. When the ribs are aligned, okay, that will provide a continuous discontinuity, and that is not preferred. All the ribs are to be staggered. Next. So that is one thing. There is a sudden change in cross section. This is better because I have provided a fillet. This is much better. I have ensured a same thickness here. So you have to think whether my design could be modified. Next slide please. So when you have a rim, this is not preferred, this is preferred. Similarly, again the thickness is made that the thickness is very high and a very small thickness. Here the thickness is made very uniform. Next slide please. This is a blind hole. A blind hole. So this is for designing components by machining. So earlier I have talked about injection molding. Injection molding is mainly for plastic parts. Then I have talked about sheet metal parts. Then I have talked about casting. Now I am talking about metal cutting. Now a blind hole with a flat bottom is very difficult to make because your drill bit always leaves a conical surface like this. So if it is acceptable, designer must provide scope for this. Next slide. Now, when you make holes, the drill bits are available only in standard sizes. So don't go for, it is in inch. If you are following, even now we are following the British drills also as well as the international standard drill bits. Okay. Now you should use wherever possible holes of standard diameters only. So 5/8 hole, 5/8 of an inch is what is specified here. Generally we should follow millimeters only, but in machining still we do follow the British system also, the English system also. So this is the 5/8 of a hole. That is a standard drill bit available. I can easily make this hole. If you say it is 0.627, I don't have a drill bit for that. I should go for a special manufacturing process like boring, which is expensive. Next. So you don't see, suppose you don't design something which is very difficult to machine. Okay. You also, if you want to have some hollows on overhangs, it is very difficult to machine because the overhang may not be able to withstand the cutting forces. Next. That will be explained better I'll come to that. There is another slide which explains that very clearly. This is, you have to drill a very deep but small hole. Again, very, very difficult to make. Because please imagine a drill bit is a cantilever. Cantilever is something which is relatively weak. Suppose I have a huge weight. Here and then I have to hold like this. It will be very painful for me. Yes or no? Suppose this is 10 kg, I have to hold it like this. Okay, it will be very painful for me. What will be the tendency? I would prefer, I will be much more comfortable if I could rest my hand here. The same 10 kg, if I could rest my hand somewhere here, I will be more comfortable. Yes or no?
Yes.
Why? At this position, this is a cantilever beam. On the other hand, when I rest it here, it is a simply supported beam. You can find out the support reactions and then find out that you know how to find the support reactions. I can find out that the force acting at my joint is much lower when I could rest it like this. Similarly, but please believe me, a drill bit is a cantilever. It cannot become a simply supported beam. When you make the cantilever very long, it may not be able to withstand the cutting forces and it may break. If it breaks inside, it is very difficult to take it out. Because the drill bit would have tried to bite the metal and in that process it would have broken. And it is very, very difficult to take it out. It's almost impossible. You may have to scrap. So, avoid long, narrow holes. Next slide please. So, very small radius, don't provide a very small radius here, it is impossible to machine it. Next. Don't provide a too thin a wall. If you provide a very thin wall, the cutting forces itself might break that wall. Next. Similarly, don't try to drill a hole at an angle. Now, please remember the drill must always come perpendicular to the surface. If you want to drill a hole, the drill bit must be perpendicular to the surface. If you want to drill a hole like this, on a surface like this, it is very, very difficult. The drill bit must be positioned always perpendicular to the surface when you want to drill. Now you have to, don't position the hole too close to the wall. That will be causing a lot of problems. Next. Because if it is too close to the wall, you cannot access it. You don't have an access to this point. If you made a hole here, then you cannot access it. That head is colliding with your design. Next slide. Similarly, if you have a long thing, if you drill it, this is a long cantilever beam, under the cutting forces, it may get bent, it may vibrate, it may break. Next. Similarly, this is a very long tool, and a long tool may again vibrate. Next slide, please. So don't provide change in directions for the hole. This cannot be machined. It has to be cast. The thing in the left, it cannot be machined. It has to be cast. On the other hand, I can drill one hole here, another hole here, third hole here. Probably I may have to plug it at the points that I want. So I can drill one hole here, another hole here, another hole here, and plug it somehow so that I can obtain the same shape. Okay, I cannot ask my drill bit to bend after some distance. No, that's not possible. Next. So here, when you have a cylindrical surface, I don't have any reference. I cannot even hold it. I cannot have a fixture for this. So try to have some references. Have a flat surface here. It will be easy for me to reference it. Next slide. You don't provide outside rounds, which are very difficult to machine unless we have a CNC machine. Next slide. Now, go back. Now, all that we have seen is, if you want to summarize whatever I have discussed, okay, in this session, you have to accommodate the manufacturing requirements also in your design. Because anything that you design is meant for manufacturing. The manufacturing engineer is going to have some headaches, some difficulties. You also reckon that, you also take that into consideration so that your design is easy to manufacture. Do you understand? But you will be able to do this only when you understand all the manufacturing processes. That you will study in your manufacturing technology 1 and 2. You will learn that in your labs. So once you know all the manufacturing processes, so you think as a designer, you think for a moment how this part is going to be manufactured. Will there be any difficulty in that? Can I modify my design so that the part can be manufactured with relative ease? So that is what this is all about. The next I am going to talk about, the next 5-10 minutes I am going to talk about, next slide please, design for assembly. So when parts are manufactured, these parts are to be put together. Okay, these parts are to be joined together. So what are the traditional methods of joining? The traditional methods of joining are by using bolts and nuts. You can bolt two pieces together. You can use rivets. You know about rivets? Okay, your mini drafter had a rivet. Okay, the writing portion of the chair that you have here, they are joined together by means of bolts and nuts. Your chair is fixed to the ground. The chair in which you guys are sitting is fixed to the ground using bolts and nuts. Okay, so joining two parts by bolts and nuts is one way of doing it. Right? The next one is riveting. Riveting, the links of a drafter that you have used, they are joined together by means of rivets. Okay? Riveting is a metal joining process in which you have two parts to be joined. You have two parts to be joined. You drill a hole. Are you able to see this? Okay. You put the rivet. You have two plates to be joined. You drill a hole. You put the rivet. Then you hold the top portion and then deform the bottom portion. Okay. Then that operation is called riveting. The skin of an aircraft is joined to the frame by riveting. The skin of a bus, the outer skin of the bus, in traditional bus building, I am not talking about Volvo and other things. In conventional PTC bus, okay, the skin is joined to the frame by means of riveting. Is it okay? So riveting is one way of joining things. Then you have press fits and snap fits. I don't know. Some of you might have used a pencil box, at least in your school. Hey, anyone having pencil box now? Hey, it is not. It's not bad to have a pencil box. Anyone having? No. Okay, the pencil box, they close by what is known as a snap fit. You can hear a snap.
Cell phones.
Beautiful. Cell phones, I don't know. Yes, the battery part. Beautiful. Good example. Okay, the battery, there is a sliding thing and then it snaps and then it fits. That is called a snap fit. Are you able to appreciate what I am saying? Okay, there is a cover. There is a cover at the back. It fits by a snap fit. Okay, it snaps. You can hear the sound also at times. Okay. Then you can join together by means of spot welding. You can do welding. You can join parts together. Nowadays, very good adhesives are being developed. So you can even join metallic parts together by means of good adhesives. Okay, when I was a student, okay, my teacher used to ask, how will you join these two parts? What he is expecting is by welding or by riveting by bolts. If you don't answer, he will shout at us. I remember so clearly. When I'm not answering, okay, by rivets or by bolts or by welding, earlier, 30 years back, they used to ask, will they join it using a gum? But today it has become a reality. You can join engineering parts, load-bearing parts by means of good adhesives. Now the challenge in designing nowadays and challenge in design for assembly is my part must facilitate automatic assembly. Please believe me, the most difficult thing to automate is assembly. The most difficult thing to do by automation is assembling parts together. I can automate machining, I can automate complicated motions, but it is very, very difficult. See, bolt, there are robots which are available to perform many complex parts. But believe me, there is no robo which can tighten a bolt. It is very, very difficult to make a robo which can tighten a bolt. You think about it, probably you will appreciate it better. Okay, take this statement and then think about it. It is very, very difficult to make a robo which can tighten a bolt. It is very difficult, I won't say impossible, it is very difficult to have a robo which does riveting. On the other hand, it is easy for me to have a spot welding robo or a welding robo or a robo which applies adhesives and then join parts. So assembly automation is very, very difficult, and I have to consider that in my design. There are very few parts that are completely manufactured without the involvement of human touch. Okay, very, very few products that are manufactured completely by automation. Total products. Even in automobile manufacturing, many things can be automated, but still in the assembly line, you require people. I am going to show you a few assembly lines at the end of the lecture. You will appreciate the difficulties involved. Now, another important thing when you design, so when I designed the shaft, I provided what is called a chamfer here. When I designed the shaft, I provided what is called a chamfer here. Okay, you have a shaft. The shaft will have a chamfer. When I design a hole, the hole also will have a chamfer. It has many purposes. A chamfer has many purposes. As I told you, a sharp edge is also a weak edge. So you want to avoid a sharp edge. If I don't provide a chamfer, you have a 90-degree edge here, which is sharp, which may damage. So you provide a chamfer. All engineering parts, they will have multiples of chamfers. If I take this pen, okay, if I see the tip here, it will have a chamfer. Why it does have a chamfer? Otherwise it may scratch, it may damage, it may cause a scratch on my hand. It will have a chamfer. You can see any cylindrical part, it will have multiple chamfers or radius. Now, from the assembly point of view also, a chamfer is having a significance. If I don't have a chamfer here, if I don't have a chamfer on the hole, imagine putting them together. It will be very, very difficult. See, the bolt, the end of the bolt will have a chamfer. The top of the nut also will have a chamfer. Why? Because when I try to assemble them together, they will automatically align. They will align much more easily. If you don't have a chamfer on a bolt and a nut. If you try to assemble, it will be very, very difficult to put them together. Okay? So, providing a small chamfer, it helps you a lot. And why I am telling you is, the assembly practices are to be reckoned, or to be considered while you are designing. Next slide please. So you have a liberal chamfer here. This facilitates easy assembly. Now next I have two videos on typical assembly lines. Okay, how one is an assembly line of an engine and the other is an assembly line of a Hyundai factory, a car manufacturing company. These two assembly lines you see just to get the issues involved. Okay, probably with that we will call it a day. And 1 minute, sir, before we go to that, I want to give the term assignment. Okay. Now I'm going to do two things. The first assignment for this term, weekly assignment, I'll give you 5 products. 5 products. Okay. You have to identify how these products are manufactured. You just write a page. How these products are manufactured. Okay. One is the pen cap. Number 2, what I want you to do is, you have to identify how it is manufactured and how the design is slightly modified to facilitate this manufacture. 2 things. How it is manufactured. Number 2, design modifications, design features, because modifications you may not know what was earlier and how it was modified. Design features that facilitate easy manufacturing. Okay. Pen cap. Okay. Number 2 is cylinder head. A cylinder head of an engine. Okay. A cylinder head of a water-cooled engine. Water-cooled engine. The cylinder head of a water-cooled engine. Okay. The third thing is a bolt. Fourth one is a bolt. How is a bolt manufactured? We have seen it. Okay. What design modifications are performed so that the bolt can be manufactured easily and it will function better? The fourth one is a silencer tube. The fifth one is a gear. So this is for roll numbers ending with 0. I'll change it as 0 and 5, 1 and 6, 2 and 7, 3 and 8, 4 and 9. Okay. Is it okay? This The another assignment is, okay, another assignment is, you have to generate concepts. You have to generate alternative concepts, at least 3 concepts to achieve these functionalities. Okay. The first functionality is convert rotary motion to linear motion. You have to convert a rotary motion. A shaft is rotating, but with that shaft, I want to move something. You have many practical problems, applications for this. You have, in a lathe, you have a shaft which is rotating, the output of the motor. But with that, you want to move a carriage. Okay. So, how to convert a rotary motion into a linear motion? 1 and 6, converting linear motion to rotary motion. Why do you want to convert a linear motion into rotary motion? Say in a piston. Your piston is reciprocating. It is executing a linear motion. But that is useless. It is going up and down. But when it is converted into a rotary motion, I can use it for many applications. So please don't explain to me, in this assignment, please don't explain to me how a piston works. I want you to generate multiple concepts on this. You generate 3 to 5 ideas, different ideas, let it be wide, let it be something even which is not workable. But generate ideas, wilder the idea, better. Like in your brainstorm, you generate ideas, okay, which will convert a linear motion into a rotary motion. 2 and 7. 2 and 7. Increase torque. I want a huge torque necessary. How can I have to have huge torque? To have huge torque. 3 and 8 to get 1 lakh RPM. Many times you require 1 lakh RPM. There are many applications. Suppose I want to drill a 0.5 mm diameter hole. Take it from me, you require about 60,000 RPM. I want to grind a very small hole. Again, you require 1 lakh RPM. There are many applications which require huge RPMs. Okay, how to generate huge RPMs? To amplify force by 100. I want to amplify the applied force by a factor 100. I can apply only 1 Newton at a particular point. But at some other point I can apply only 1 Newton, but at some other point I want 100 newtons. So how to amplify a force? You conduct a sort of brainstorming within yourself. You conduct a brainstorming within yourself. This is again not a team exercise. It's an individual assignment. You conduct a brainstorming within yourself and then come out with some ideas. Minimum 3 to 5. And no sharing of resources. You have noted that. So these are the 2 assignments which you will be submitting within, say, before next Tuesday. Now we have the videos. Facility, you can see the various parts being manufactured and assembled. What you have just seen is the engine seal. Between the engine head and the body, there will be a seal which is coming. You have seen that part. You have the Hyundai manufacturing. So here you have the car assembly happening.
Welcome to Let's Talk Wheels TV. I'm your host, Mike Herzing. If you are ever near Montgomery, Alabama, you owe it to yourself to stop at the Hyundai Motor Manufacturing America plant to take the free tour. Here's a short video that shows how they build these great cars.
Folks, you can see this Hyundai plant here. It's a little noisy, but bear with me. If you look right here, you can see the robots welding the up to 2,100 welds on the bodies here. This is amazing, folks. Check it out. I mean, you don't get to see this. This is amazing. This is one of the highest quality and highest tech plants on the planet Earth, right here. Won the Harbor Award for technology and quality.
You can see here the robots doing the real back-breaking and repetitive work. They're also doing it at a high speed. That eliminates human errors, and that obviously makes a big difference in quality, which is what this plant's known for. So take a look at these things in action. See, as the team member comes up and looks at the computer printout to see what each vehicle gets, starts marking everything. Now the doors have been removed, and there's also protective coverings over the fenders. That just protects from any other damage that might happen in an accident. You can see how she goes in and checks everything out, gets it ready for the next person. Also, you'll also notice how each vehicle is on a platform. They raise and lower depending on the height of the particular team member. This vehicle has just had the dash put in. Now you can see them underneath. They're tightening up the subframe. Now, obviously, that's a specific torque, so the computer takes care of that. Also, as everything is raised up into place, you'll see the engine and transmission, the exhaust system, and the differentials and the rear suspension all added on here. You'll also see the struts would go right into place. Everything is just all timed exactly. And the neat thing about it is all these guys here and gals, they call them team members, all have smiles on their faces because they're enjoying their work. Once again, you can see the vehicles, everything is raised up into there. Nobody has to reach or bend down or do anything excruciating. You can see this team member move on each side, putting in the rear brake cables and things like that. Everything is done precise. All those wrenches are using to a specific torque. Here they are right now putting in the inner fenders. Those are plastic inner fender liners.
Okay, this is Mike Ersing again. Hey, we're at the Hyundai plant. We're about 2 steps past that, where we were before. Tell you what, you can see these cars being built. These cars can be raised and lowered. This is where they're putting in the seats. It's amazing, guys. You don't get to see this kind of stuff. Once again, Let's Talk Wheels is bringing it to you. It's a little noisy, but this is a working plant. They are not stopping for us. And this is still one of the highest tech plants on the planet. Check it out. Just take a second and look at this. You're seeing these Sonatas, and we have Elantras and Sonatas and things like that being built. Here's a whole run of black ones. You can see the tags on the front. That tells what interior each one gets. Like that one's got a black interior. The next one's got a gray interior. Those are unloaded off the truck in that order.
That's where they get the term just-in-time manufacturing. Everything is unloaded off the trucks in order, just in time. Because there are no warehouses, everything has to be done correctly. Now, otherwise, if they mess it up, you're going to have a purple car with a green interior. We would never want that. That's why this all works. Here we see the robots getting ready to install the windshields, which is something we need to do. And next, we're going to see the organization board, or the status board they call it, where the team members can look at the status of the vehicle across the line. At this station, the robots, as the car comes up, will place the wheels there for the team member to line them up and put them on, and then another machine goes and tightens the lug nuts to a specific torque. Wouldn't NASCAR guys love this? Next, you can see the team members doing the thump. They're seating the windshield and the front and rear windows down, which is a good job to have if you ask me, and they do it without breaking anything. That's the best part. I don't know that I could do that. As much as everybody touts computers and robots, it's still the personal touch that makes the difference, even here at Hyundai Motor Manufacturing USA. We're going to make a side trip here to the engine plant where we can see the robots picking up the crankshafts. That is the main engine component of the four-cylinder engine. You can see it. It'll be moving along here in just a moment. You can see one of the other people here. Here it is. It pulls the crankshaft, which actually weighs a few pounds. Sets it in the box. It's been cleaned and polished and balanced and magnetized. Next, you can see the plant. This thing is pretty immense, though. These are the four-cylinder turbocharged engines that they use in the Elantra and the Sonata. Some of these engines go over down the road to the Kia plant and used in some of the Kias. So this plant makes more than just stuff for Hyundai. There you go. Yeah.
Okay, folks, we're at the end of the tour, and you can see right here, the vehicles are going to drive, but they're just been started for the first time. It is just going to move for the first time. These bumps right here are not speed bumps. Those bumps there are to waken up the suspension because it's the first time it's moved. They're honking the horns. They're driving them. There you go. You can see the vehicle free up. And that vehicle was just born. You witnessed the birth of a Sonata right there. It is now going to a dynamometer to be run for a minute. Then we'll go out and be on a 2.3 mile test track. The vehicle, these vehicles, every single one of them, not just every fourth or none of it, every single one of them is driven on a test track by a professional driver to listen for squeaks and rattles and things like that. If they find a problem, it is off the line. It gets sent back and figured out what's wrong with it. Folks, this has been a great day, and I just want to say thank you for joining us today on Let's Talk Wheels.
Thank you.